Hello, this is the start of the next batch of exam questions that we're going to be doing on classical mechanics. Most of these are to do with force. There's a few other little bits that creep in here and there, but really we're just blasting through our force knowledge. So let's crack on with the first one. We've got energy and work done are scalar quantities, have the same unit as each other. State two other scalar quantities in physics which have the same unit. Okay, there's loads of them. I'm going to stick to the ones in classical mechanics because they're the things that we've been looking at so far. Well, we've got moment and torque. That's a good go-to one where they're the same. Moment and torque of a couple. Torque of couple. Other good ones for same units are things that get into stuff with Young's modulus because we've got a lot of it where the strain bit doesn't have any units, so that means that we've got pressure, stress, and Young's modulus all have the same. So you can pick any combination of those. We can have pressure and stress, pressure and Young's modulus, stress and Young's modulus. So that's 3 more pairs there. So all in all, we've got 4 pairs there. So you can pick any of those. But yeah, it just drops out nicely from the Young's modulus one because you've got that FL over AX. This bit, the strain, doesn't have any units, does it? So here we've got the stress, the pressure, the Young's modulus, all the same thing. Part B, two forces A and B act through the same point in an object. Okay, so they're shown in a graph. Right, we don't normally look at forces on a graph. They've split their X and Y components here and then just plotted them as vectors on this graph. So I mean, they could have said, A is, what is A? 2, 3. We could have written it like that, and we could have said, well, B is 6, 2. Or we could have written it in IJ. They just happened to put it on a graph here. Right, what do they want us to do? Use figure 2.1 to determine X and Y components of the force B. All right, we've just done that there. So 6 and 2. And then determine the magnitude of the resultant. So the resultant is 8, 5. We're just adding those together. So the magnitude of the resultant is going to be the square root of 8 squared plus 5 squared. So the square root of 89, which is, just putting, it's going to be 9 and a bit, and at 9.4 newtons. We've got a jet of water from a hose pipe in part C. Air resistance is negligible as always. Maximum point at Y. State the direction of the force acting on the water at Y. Well, it's the same as it is everywhere else. It's down because we just got projectile motion going on here. Describe and explain how the horizontal component of the velocity of the water varies from X to Y. Well, it doesn't. It's constant because there. So this is the usual thing. You want to put in that there's no net force horizontally going that way. Therefore, the acceleration equals 0. So just the usual bits and bobs put into a sentence. Describe how the vertical component of the velocity of the water varies from point X to point Z. Right, okay, so as it goes from one side to the other, well, at Y V equals 0. We know that bit. On the way up, I mean, you can put signs in on, I mean, I'm going to say the magnitude. The magnitude of V decreases from X to Y. And you could put in something like it's positive and decreasing. So you could have positive on there, but you have to decide then which way is going to be up. But then we can say the magnitude of V increases from Y to Z. So either do it that way or say positive velocity decreasing and then negative velocity increasing in magnitude on both of those. In magnitude. Because otherwise you get this whole thing of what does it mean if you've got an increasing negative velocity? Does that mean it's getting more positive or is getting more negative? So you want to say which way round it is. So just having these magnitude signs in just make it a bit clearer. Then you don't have to worry about which way is up. Cool, so that's the first question. Right, next one, we've got the path taken by an aircraft as it flies from A to nowhere. Oh, this must be B that has just disappeared off of here. Okay, path from A to B, right, so it's taken this sort of jinking route. Distance of 1 centimetre represents 50 kilometres. Aircraft takes 25 minutes to travel from A to B. Use this to determine the magnitude of the average velocity. Right, okay, as it travels from A to B. Right, well, this has all been rescaled, and it's relatively hard to measure this off of the screen. I'm just trying to find a ruler, which I can't actually find. But we're wanting to measure just the straight line going from A to B. So I'm going to do this in a, let's just chop it up and say 1, 2, 3, 4, 5, 6, 7 maybe. If you have a look at a mark scheme of this could well be different because I've rescaled this from the size it would have been on the paper. So 7 centimetres means we've got 350 kilometres. That's our displacement, because for looking at the magnitude of the average velocity, we have to look at displacement, not distance. So you don't want to measure the distance up here and down there, because that's going to give us the average speed, not the average velocity. So we got that. Now we have to, that's our distance, so we have to divide by the time. So let's put it in meters per second. 350 and then 3 more zeros divided by 25 minutes. So 25 times 60. Get rid of a couple of zeros already. 6 25s is 150. Get rid of another couple of zeros. Divide by 5. So multiply by 10 and divide by multiply by 2. I mean divide by 10. So that's 700 over 3. 700 over 3 is 2 1/3 times 100. So 230, say, meters per second. Then, without doing any calculations, explain why the average speed of the aircraft is not the same as the magnitude of the average velocity. Right, so for this, we have to say distance travelled is greater than the displacement from A to B. And then if we were going to really hammer it home, we could say speed uses distance travelled, velocity uses displacement from A to B. So if the distance travelled is greater, we're going to get greater speed. Cool. IO is one. All right, we've moved away from aircraft then. We're now on IO, going around Jupiter. Travels at a constant speed in a circular orbit of that. And it takes that long to orbit. Calculate the speed of IO in its orbit. So that's going to be distance over time. So speed equals 4.2 times 10 to the 8 multiplied by 2 pi. That is assuming it's got a, oh, it does say circular. It'll be close to circular. So that's our circumference of the circle divided by the time, 1.5 times 10 to the 5. Get rid of those, make that a 3. And yeah, I suppose we just have to type all this in now. And we are getting 1.8 times 10 to the 4 meters per second. So that was straightforward enough. Now we got active volcanoes producing jets of sulfur with a velocity of 1.3 kilometers per second, rising 470 kilometers above the volcano. Calculate the constant acceleration of freefall. I suppose we could leave that in. They've given us kilometers twice, but it's going to give us a small number if we stay in kilometers. I mean, that's fine, I suppose, but we would expect the G on Io to be less than it is on Earth, seeing as Io is smaller. So I'm gonna flip over on this, and let's use so v squared equals u squared plus 2as. That's going to be fine because we know we're hitting the high point at 470. We don't worry about magnitude on this. We can just say it's coming downwards, and we can say that u squared, so that's 1.3 times so kilometers per second. So we're going to want to add in a 3 there. That's to put it into meters, and then we want to square that. Is going to be equal to 2as, right? So 2 times a times 470 times 10 to the 3. Okay, so we can get rid of that 10 to 3, 10 of to the power 3 with one of the ones on the other side. So the take that off there and square that. So the acceleration is going to be 1.3 squared times 10 to the 3 divided by, is that 940? So we've got 1.3 squared divided by 940 is 1.79 bits times 10 to the minus 3, and that cancel with that 10 to the plus 3, so that looks like a good choice. So we've got 1.8, give or take, meters per second. It's actually 1.80 on that, but I don't think they've only given us a 1.3 here. So yeah, so let's stick with 1.8. There we go. All right, next up we're looking at drag. We've got a drag force acting on a car traveling at speed v is given by this equation. Let's make that a little bit clearer, so it's a bit hidden under the text there. So KAV squared, where A is the area of the front of the car, show that a suitable unit for the quantity K is that. Okay, so we want to rearrange things and dump the units in. So K equals F over AV squared. So put in the units in on this. We've got, well, I suppose let's put in newtons then. So kilograms meters per second squared, that's our force at the top. We need to divide that by meters squared, and then we need to divide that by meters squared per second squared. So let's then start cancelling a few things. Well, those per second squareds disappear top and bottom. We lose 1m top and bottom, and we're left with what it says in the question. We got kilograms meters to the minus 3. Table tennis ball experiences drag as it travels through the air. Here we go. We got figure 6.1 shows the ball in 3 situations, A, B, and C. The ball has weight W, drag force is D. On figure 6.1, draw an arrow to show the direction of travel of the ball in situation A. Right, well, drag is always directly opposed to the motion. So we're going to want to have direction of motion to be directly opposite the drag. Situation B, the magnitude of the weight and the drag are the same. Explain whether or not the ball is traveling at terminal velocity. Well, in terminal velocity, then we've got no net force. So here, well, we clearly do. So so we can say it's not terminal velocity because there is a net force. There is net force. So that's fine. They've tried to catch you out there because, of course, in terminal velocity, if the drag and the weight were opposed to each other, directly opposed, and they cancelled out, then fine. But you've got the drag going in a different direction there, so they're not opposed. Describe and explain the motion of the ball in situation C. Okay, describe and explain. Right, so the ball is moving upwards. So it's moving vertically upwards because the drag is vertically up because drag is down. So the motion must be in the other direction. So then we could say it will slow down because there's a net downwards force. So yeah, we could. There's not really much else to say there. It will slow down because of net resistive force. Resistive force, or net downward force is probably better because you've got the weight in there as well. I suppose they're all resistive forces, so it doesn't really matter which way you want to put it, I think. But downward force is probably a little bit safer maybe on that. Figure 6.2 shows a DVD held above the ground. DVD is dropped from rest. Circular face remains horizontal. DVD does not reach terminal velocity before it hits the ground. Describe and explain how the acceleration of the DVD varies. Right, okay, so we're just talking about the acceleration. So we'll put something in here. So initially, the acceleration equals G because drag equals 0. let's call that a capital D. After this, of course, we can then say that the drag will increase as v increases, or the speed increases, whichever way. Let's put the magnitude of v increases. So the drag increases as the magnitude of v increases. So therefore, the net force will decrease because the drag is opposing the weight. Therefore, net force is less than the weight. Therefore, the acceleration is less than g and decreases. So acceleration decreases less than g, but it won't hit zero. So we can say when it hits the ground, the acceleration will still be positive. It won't reach zero. So maybe worth putting that in as well. Acceleration will not reach zero before the ground, because they've told us that it doesn't reach terminal velocity. So yeah, it's a nice collection of stuff there, just talking about drag and how it works, how things vary from case to case.